Welcome back, children. So today we'll be studying about Doppler's effect of electromagnetic radiation. Okay, here we'll be discussing about how do we define Doppler's effect. Then we will prove that Doppler's effect in light is symmetric in nature. We'll look into the expression for how to calculate the change in frequency or wavelength due to Doppler's effect. Then relativistic Doppler effect. And at last we will study some of the applications of Doppler's effect. Coming to the definition of Doppler's effect, see, we have already studied it in case of sound waves, that we have defined it as it is an apparent change in frequency due to relative motion between source and observer. So when there is a relative motion between source and observer, you will observe a change in frequency, and this apparent change in frequency is nothing but called as Doppler's effect. And in case of sound waves, we have discovered or we have derived the relation for apparent frequency. Okay, what is the formula for apparent frequency given by n dash is equal to n into v minus v naught by v minus vs, where v is the speed of sound, v naught is the speed of observer, and vs is the speed of source. And what is the sign convention we have taken? If source is taken on your left hand side and observer on the right hand side. In such a case, which is the positive direction of Vs? If source moves towards observer, it is positive. If source moves away from observer, sign convention is negative. Similarly, if observer moves away from source, V0 is positive, and if it is moving towards the source, V0 is negative. So with this sign convention, we have proved that sound waves, in case of sound waves, Doppler effect is asymmetric. Okay, let us look into it once again. The meaning of asymmetry is the frequency apparent change or apparent frequency observed is not the same when observer moves towards the source or source moves towards the observer. See, in the first case, source is stationary. Source is not moving. When observer is moving towards the source, so we know V0 is negative, Vs is 0. When you substitute in the formula for apparent frequency, we get apparent frequency as n dash is equal to n into V plus V0 by V. Now we'll take opposite. If observer is at rest and source is moving towards the observer, in such a case, V0 is 0, Vs is positive. What is the apparent frequency we have got? N dash as n into V by V plus Vs. Now you observe the two equations. The first equation, it is V minus V0 by V into n. In the second case, apparent frequency is n into V by V plus Vs. So even if observer and source are moving with the same speed, these two expressions are different. This is called asymmetric nature of Doppler's effect in case of sound waves, because sound waves are having a speed of 330 meter per second. Depending on which direction observer is moving, the relative velocity of sound with respect to observer is going to change. So due to this change, we will observe that in case of sound waves, Doppler's effect is asymmetric in nature. Coming to Doppler's effect of electromagnetic waves, or in case of light, it is symmetric. The reason here is, since electromagnetic waves travel with a very high speed, so we know the speed of electromagnetic wave in vacuum is 3 into 10 to the power 8 meter per second. And since this speed is much higher when compared with the speed of source or observer, this will lead to symmetric nature of Doppler's effect. So we know that if this is the observer, if I take O as the observer, whether observer moves in this direction as shown by the arrow, or this, or this, or in this direction, speed of light with respect to him will always be 3 into 10 to the power 8. So there is no change in the speed of light even if observer is moving. Okay, because observer speed is much smaller when compared with 3 into 10 to the power 8 meter per second. Because of this nature, we will prove that Doppler's effect is symmetric in electromagnetic waves. So we will use the same formula that we have derived for sound, where v was the speed of sound. Now that is replaced with c. So here c is nothing but speed of light, 3 into 10 to the power 8. Vs is the speed of source, v0 is the speed of observer. Look at the first case. When source is at rest, see, I have kept the source at rest. Observer is moving towards the source. So V0 is negative. V0 is negative, Vs is 0, V is replaced as C. Look at the apparent frequency. We know the general formula, n dash is n into V minus V0 by V minus Vs. Put the conditions, V0 as 0 and Vs as negative. Okay, so when you put Vs as 0, when you put Vs as 0 and V0 is negative, apparent frequency is n into C plus V by C. Okay, that's nothing but n into 1 plus V by C. I repeat, what is the apparent frequency? When source is at rest and observer is moving towards the source with a speed V, it is 1 plus V by C into n. Now let us look at the next case. Apparent frequency if observer is at rest and source is moving towards the observer. So in such a case, observe the formula. Okay, we will get n dash as n into C by C minus V. Okay, since observer is stationary, V0 becomes 0, V is replaced as C and Vs is replaced as V. Now I will use binomial approximation. Okay, in the next step you can see I brought this C to the denominator. You will get n dash as n into 1 by 1 minus V by C. 1 by 1 minus V by C can be written as 1 minus V by C whole to the power minus 1. And just now I told you V is smaller when compared with C. If V by C is very less than 1, using binomial approximation, n dash is n into 1 plus V by C. See, even in the previous case we have got the same formula. So the answer for apparent frequency is going to remain same, whether observer is rest and source is moving towards the observer, or source is at rest and observer is moving towards the source. So this is called the symmetric nature of Doppler's effect in case of electromagnetic waves. It is different in case of sound, but frequency remains same in case of light. Now just now we have seen the expression for frequency. Okay, when observer or source and observer are in relative motion, whether they are moving towards each other or away from each other, then what was the relation we have got just now? N dash is n into 1 plus V by C. Now because we want to find out what is the change in frequency, modify the relation. N by n dash is equal to 1 plus V by C. Okay, bring the 1 to the left hand side and simplify it. Change in frequency by original frequency. We have got the relation as V by C. I repeat, change in frequency is delta n is equal by n is equal to V by C. So here V is the radial velocity or velocity of the substance with respect to earth or with respect to observer, source with respect to observer. C is speed of light. So delta n by n is equal to V by C. Okay, we know whenever frequency decreases, wavelength will increase, and if frequency increases, wavelength would decrease. So because of this, you can modify this formula for Doppler's phenomenon as this relation. Delta n by n is minus of delta lambda by lambda. Delta lambda is the change in wavelength, delta n is the change in frequency. Should be V divided by C. So you can make use of this relation when V by C is much lesser than 1. Now look at what is Doppler's or applications of Doppler's effect. So to understand the applications of Doppler's effect, so let us start with the first application. It helps in detecting if a star or a celestial body is approaching or receding from Earth. So to understand this, assume that this is a star at a certain distance from the surface of Earth. Because we know star is going to emit white light. So when this white light is passed through a prism, okay, we get a spectrum. Since white light is composed of many wavelengths ranging from 400 to 700 nanometer, on an average, we should receive the average wavelength close to yellow color. So what should be the average wavelength received from a distant star in general? It should be around yellow color, which is average of blue and red. So we collect this light from the star and observe what is the wavelength received on the Earth. If you receive about yellow color at different intervals of time or after a certain interval of time, we can say that this star is stationary. Okay, since on an average we are receiving a wavelength of yellow color which is not changing with time, the star is said to be stationary. Look at this case, blue and red shift. Instead of receiving on average of yellow color, okay, this black line indicates that the wavelength received is of yellow color. If you receive a wavelength which is closer to blue, okay, which is moving towards violet or towards blue, then we call this as blue shift. So when you receive the average wavelength from a distant star close to blue instead of yellow, the shift is called as blue shift. Blue shift implies, because it is moving towards lower wavelengths, we are receiving a wavelength which is shorter than the original. If wavelength is decreasing, that implies star is approaching the Earth. So decrease in wavelength implies increase in frequency. If frequency is increased, we say that it is experiencing a blue shift. Blue shift implies that the star is moving towards the Earth. Then come to red shift. This is the opposite case. We expect on an average the wavelength should be around yellow color. But instead, if the wavelength shift towards red colors, that means higher wavelengths, we say the shift as red shift. Red shift implies an increase in wavelength. If wavelength of received light is increasing with time, implies the star is moving away. The star is moving away from the surface of Earth. So a red shift implies star is moving away from Earth, and blue shift, star is approaching the surface of Earth. Okay, let's look into a few more applications of Doppler's effect. It tells you about the rotation of sun. Okay, to know whether sun is rotating or stationary, we try to determine the apparent wavelength received on the Earth. Okay, if this is the surface of Earth, okay, you are on the surface of Earth, determine what is the apparent wavelength from the North Pole and the South Pole. Check whether they are equal or not. It has come out to be equal. Similarly, find out what is the apparent frequency or apparent wavelength received from west and east. It is observed that the frequency received from west is different from east. It happens only if there is rotation about vertical axis or about north-south axis. See, if suppose sun is rotating like this in anti-clockwise direction, the wavelength that we receive from the west end will be more because it's approaching towards when compared with east. So if you observe a difference in wavelength between west and east part of the sun, then this implies sun is rotating about an axis passing through north and south. So this is how we can prove whether sun is stationary or rotating about an axis. Okay, Doppler's effect also helps in proving that universe is expanding. For that, assume any celestial body. This is a celestial body. Determine the wavelength reaching the Earth. And after a certain duration of time, again determine what is the wavelength reaching the Earth. It is observed that for any celestial body, this wavelength is continuously or gradually increasing. This implies that all the particles of the universe are under expansion or are going away from the Earth. This implies that universe is expanding. So using Doppler's effect, we can prove that universe is expanding. Next, Doppler effect also gives you information about the nature of Saturn's rings. So we know Saturn has the gaseous particles revolving around it or orbiting around it. Previously, these rings were considered to be solid rings. Okay, this whole ring is considered to be one solid material. And if it is a solid material, determine what is the apparent wavelength from the inner and outer edges of the rings. See, this is the outer edge and this is the inner edge. I'll call the apparent wavelength as lambda 1 and lambda 2. Okay, we know inner edge is close to Saturn, outer edge is away from it. Since it is close, velocity should be more for outer surface and velocity should be less for inner surface. Okay, if it is a solid ring around the Saturn, that means Saturn is rotating, these rings are rotating about this axis. We know V is equal to R omega. Since omega is constant, the velocity that you receive or velocity of the ring, outer ring, should be more when compared with that of inner ring. If velocity is more, lambda 1 should be greater when compared to lambda 2, because apparent frequency or apparent change in wavelength, just now I told you, delta lambda by lambda is equal to V divided by C. But practically it was observed that lambda 1 is less than lambda 2. If you consider Saturn ring to be a single solid continuously revolving, according to Doppler's effect, we should get lambda 1 greater than lambda 2. Wavelength, apparent wavelength from outer ring should be more than inner ring, since outer ring has more speed than inner ring. But practically, what is the phenomenon observed? It is reverse. Since the phenomenon is reverse, it can be understood this way. These rings are not solid rings, they are made up of particles which are revolving around Saturn. If they are considered as discontinuous particles, we know when a particle is revolving around a planet, its orbital speed. Okay, what is the formula for orbital speed? Under root gm divided by r. How is velocity related to radius? Inversely related to radius. Less radius, more velocity. More radius, less velocity. And if velocity is inversely related to radius, according to the Doppler's phenomenon, we will get lambda 1 as less than lambda 2. And this is inconsistent with the observed or a practical phenomenon. So this proves that Saturn rings are not continuous particles. It is not a continuous solid ring. It is made up of tiny particles or gaseous particles which are revolving around around Saturn. So this is one more application of Doppler's effect. And look at the last and important application. Doppler's effect helps in radar systems. Okay, as I told you, it helps in finding out whether a star is approaching or retrieving away from the Earth. So it also helps in the phenomenon of radar. Okay, in radar we are going to send one electromagnetic signal. Okay, you can see the radar device here, detector. This is the detector. It is sending a signal towards a target. Okay, say an aeroplane is moving close to the Earth or it is moving in a certain direction. Then they send one signal which is called a transmitting signal. And this transmitting signal will go and hit the object and reflect the waves back. The reflected signal is again detected by the radar. If there is a change in frequency between the transmitted and the receiving signal, it can explain whether the object is moving towards or away from the system. So this helps in finding out the speed of the target or speed of the plane, whether it is moving towards or away, and with what speed it is going to come towards the surface. So this is what or how a radar system is going to work. You can calculate the speed of the object also. But here remember one point, if this plane is moving in this direction and this is a line joining the radar and the object, this is going to tell me the velocity component. Okay, if I take this angle as theta, radar gives me the component of velocity which is along the line joining the object and the system. Okay, so remember that while you are solving the numericals. So these are some of the applications of Doppler's effect. So all put together, so we have come to the end of the class with applications of Doppler's effect.